Hello guys, how are you? This is Engineer Salase from Velo Academy and Brain Boosters, and today we came up with another video. This is chapter 7 of our series on operating systems, and without further ado, let's get into it. So as you can see, scheduling. We are going to discuss about scheduling. In chapter 6, if you remember, we discussed about the mechanisms, how the CPU gain control of the operating system, gain control of the CPU. We saw low-level mechanisms and time interrupt concept and cooperative and non-cooperative type of system, how context switch happens. And please go and refer that video. In this session, we are going to see the second type, which is called the policies, which falls under the scheduling. So just before there, if you want to see the context switch of your running program in Linux, just go and check your program and run your program and use this command, okay, sudo time v. Then it will show you the context switch, okay. For example, voluntary context switch or involuntary context switches, how many times the program, okay, in that program context switch happens, you can see. So just I brought this one just for your information. Again, before we dive in on the scheduling part, we have to discuss how this is the scheduling part will be in this area, okay, short-term scheduler, because as we can see, this is the state of again, this one I discussed in one of my video. You can go and check it, and this part is very important to understand what is scheduling. And a process can go different states: new, ready, run, and termination state. This is the common ones. In addition to that, we have wait and block state, and we have suspend ready and suspend wait. These are the general states of a process that could be. So in the new state, it is not a process, okay, it is a program. In this state, when in the new state, it is a program. It is in secondary memory. It will be picked by the operating system and will be put in the main memory. The process is about to be created, okay, in the new state. So when it comes to ready state, the process created at this state, it means the process is ready to run now, okay, it's ready to run. Now it's waiting only the operating system to choose which program, which process should be picked and run in the CPU, okay. So that will be the responsibility of the operating system and short-term scheduler. So we have two types of scheduling, preemption and non-preemption. In the preemption mode, we have a time quantum. So once that time quantum is completed from the CPU, the process will be preempted and it will be put in the ready state. This is what we call when there is priority or time quantum. In that case, this process will happen, this phenomena will happen. From the ready state to the run state, when any process picked from the ready state to the run state, this will be done by short-term scheduler with the help of the operating system. And we call it the schedule. The phenomena is called schedule or dispatch. So if the process is running, means the CPU has been allocated, now it's running. If the process is completed, if it is everything is okay, there is no IO request, then it will be terminated. But that is not the case. Most of the time the process, they will request wait IO request, okay. When they request IO request, then they will be put in the wait block state, okay. Then once the IO request is completed, then they will be taken the ready state, and from the ready state the short-term scheduler will pick and it will be run and the process will continue like that. But what we have is, as you know, the ready state, the run state, wait block state, all these are in the primary memory, in the main memory. Okay, they are in the main memory because they are picked from secondary memory and they are put here. But as you know, the primary memory, the main memory, is limited, like 8 GB or 16 GB, something like that. So you cannot put all the processes here. So what happens in the main memory with the middle term, okay, the medium term scheduler, some of the processes which are put in the wait and block state, they will be taken into suspend wait. So they can wait in the suspend wait state, okay, in the secondary memory. Then when they have time, then they can be resumed again, okay, in the wait. So when they complete their request, they can be taken to the ready state. So they can be in the wait block state, or we can take them from suspend wait to suspend ready state. The same thing happened here, because when the process picked from new to the ready state, again ready state is in the main memory and it doesn't have much memory. So what happens is, some of the process will be suspended into suspend ready, and when the space is there, then they can be resumed and they can continue. The same thing is true from IO operation. From suspend wait, they can take into suspend ready, and from suspend ready they can resume to ready state. That is what the whole idea, okay, the whole idea. And we have long-term scheduler, short-term scheduler, mid-term schedulers. So long-term scheduler pick process from new state to ready state, as you can see, from new state to ready state. It also decides the degree of multi-programming. Multi-programming means the maximum number of processes that can be reside in the ready state. Sometimes 100, sometimes 50, it depends on the system. So the degree of multi-programming will be decided by this long-term scheduler. So short-term scheduler, it will pick from ready state to running state, and mid-term scheduler will take processes from wait block state to suspend state, or from suspend state to from ready state to suspend state. So these are the three types of schedulers. These are the state types: new, ready, run, termination, and wait block, suspend wait, suspend ready. These are in the main memory: ready, run, and wait. And this suspend ready and suspend wait in the secondary memory. And the most important thing in this area is important discussion. For example, some processes are CPU bound, some processes are IO bound. So if the performance of the system and CPU will be depend on the decision taken by long-term scheduler. If the long-term scheduler picks more processes, only for example case 1, if the long-term scheduler choose more IO bound processes, there will be more and more context switch. As you can see, if the long-term scheduler chooses all IO bound processes, then the process will come here, then after some time it will come for IO, again another process will come, then IO, then context switch will be there, and utilization, CPU utilization will be low. Again, case 2, if the long-term schedule more CPU bound will be maximum, but the process in the wait state will face starvation. What happens if the CPU bound process are chosen by the long-term scheduler? It will be all the process will be CPU bound. So any process which come for IO operation will be wait for long. This phenomenon is called starvation. So long-term scheduler should choose a mix of CPU and IO bound process. The frequency of this scheduler's call will be: short-term scheduler will frequently call. Second, the medium-term scheduler will be frequently called, and then last, long-term scheduler frequently be called. So this is the main idea. So now when we talk about scheduling, the scheduler will be here in the short-term scheduler. So it will be easy if you put this in your mind, then we can go. So what is scheduling policy on top of the low-level mechanism. Low-level mechanisms we discuss in the unit 6. Okay, limited direct processing. So in that we see that how context switch happens, whether by the process itself, by sending a system call. Okay, because it assumes that when a process runs for long, they will send a system call, and through system call the operating system will get access to the CPU again, and that was the idea. And the second is time interrupt, because that the interrupt will be there, and through interrupt the operating system will gain control of the CPU. Okay, so cooperative and non-cooperative type, and in addition to the interrupt system was discussed. So on top of the low level mechanism, we have policies like schedulers. So how do we select which user process to run on the CPU? As we have seen here, that on the ready state we have too many processes. So which process should go to the CPU? This should be done by the short-term scheduler. So how we are going to choose, and we have a lot of policies. And what are key assumptions about the workload, what metrics are important, and what are some historical approach. This concept will be discussed. So workload assumptions. The first assumption is that let's assume each job runs for the same amount of time, all jobs arrive at the same time, all processes are non-preempted types, all jobs only use the CPU, they don't perform IO, the runtime of each job is known. So these are just an assumption to discuss, okay? Because as you can see here, when we are here, we think all the processes come at the same time and the burst time is the same, which is not true in the real scenario. But just for the case of discussion to start up, and we're gonna clear it up when we go. We will remove some of the assumptions and we will see the effect of the assumptions. Okay, we will do that. We will expand it. Okay, relax it as per the textbook language. We're gonna relax it. But for the time being, the process which are here, when they came from picked by long-term scheduler to the ready state scheduler, in the ready state, then we assume that each job runs for the same amount of time in the CPU, all jobs arrive at the same time, the processes are non-preempted, means they will continue unless they request for IO. But the issue is we don't have IO now, all jobs only use the CPU, they don't perform IO, the runtime of each job is known. So with this assumption, let's discuss a scheduling metrics for comparison of different policies. We have performance metrics. The first one is turnaround time, and we have the other one is fairness. So the time at which the job completes minus the time at which the job arrives in the system. So as you can see the formula, T turnaround means T completion means the burst time. Okay, the process came into the CPU and they complete their all the codes, whatever instruction, whatever in the CPU, then it's completed and it will go to termination. So T completion minus T arrival means the process came from new state to ready state. So when it arrives to the ready state, so when we subtract T completion to minus T arrival, it will be turnaround. Okay, so in our case, T arrival is 0 since all the processes are already arrived at the same time. And average turnaround time is critical for the group of processes. Then after that, by doing so, we will see the average turnaround time. This is one of the metrics, scheduling metrics, okay, for comparison. The second one is fairness. Fairness means performance and fairness are often at odds in scheduling. because when you think of performance, fairness may be not achieved, and when you think of fairness, maybe the performance of the system would go down. So each process can run in the CPU with fair time allocation. In the fairness assumption, you have to be fair, because one process can run long time and the other process will convey effect or starvation. It will not a problem. It will be a problem. So as a performance, we have turnaround time and fairness, because turnaround time is completion minus arrival, and fairness means the time all the process should get a fair amount of time. Performance and fairness will not come together. One may sacrifice the other to perform. So let's see the first schedule. Okay, the first schedule we have is first in and first out. That means this is FIFO. It's very known. First come, first serve. This is very straightforward and very simple. So what it does is very simple and easy to implement. Example, whichever process comes first should be take the CPU. That is what it means. So let's assume A arrived just before B, which arrives just before C. So each job runs for 10 seconds. Let's assume the burst time is 10 seconds. So A, B, C, they come at the same time at 0, but as per their order, A will run for 10, B run from 10 to 20, and C will run from 20 to 30. So when you see average turnaround time now, turnaround time means completion time minus arrival time, 10 minus 0, 20 minus 0, 30 minus 0 over 3, 20 seconds. So the average turnaround time for this particular example is 20 seconds. Now, why FIFO is not that great? Let's see. Let's relax assumption 1. Each job no longer runs for the same amount of time. Let's assume in the first example we say all processes are running the same amount of time, but now the burst time of A we make it 100 seconds. Okay, so at this time A arrived just before B, which the sequence is the same, A, B, C. Okay, the arrival time will be the same, but the running time now A will get 100 seconds. So before A completed, B and C cannot run in this situation because this is FIFO. First come, first serve. So A come first, so it should finish. Then after it's finished, B continue. After that, C continue. So as you can see, the turnaround time is completion time 100 minus 0, and this one 110 minus 0. Again for C, completion time 120 minus 0, 120 divided by 3, 110. So as you can see, it is big. In the context of CPU scheduling, the convey effect refers to a situation where a process with a long burst time is scheduled to run on the CPU, causing other short process to wait for a long time. This can happen in the situation where the CPU scheduler gives priority to the process with the longest burst time, and known as the first come first serve scheduling algorithm. So as you can see, 110. So the average turnaround time become 110. So this is typically called convey effect. The convey effect means the process which has a long time should finish until the process which has a very small amount of time cannot run. So you can see this is a problem with FIFO. So how we solve this problem? Okay, how we solve this problem? So the second policy is shortest job first. So it is obvious, if the longest process create a problem, then just bring the shortest job first and you can solve the problem. So let's see. Run the shortest job first, then the next shortest, and so on. So this is non-preemptive scheduler again. This is non-preemptive. And example, Non-preemptive means non-preemptive scheduler is a type of CPU scheduling algorithm where once a process has been allocated to the CPU, it cannot be preempted until it voluntarily releases CPU or completes its execution. In other words, the scheduler cannot forcibly interrupt a process and allocate the CPU to another process. So let's see example now. A arrived just before B, which they arrive in the same time, okay? And now what happened? A runs for 100 seconds, B and C runs for 10 seconds. So what's in the schedule, in the shortest job first scheduling type, policy 2, what it does is just instead of A, because A is 100, it will choose the second shortest, so that is B. So all they came at the same time, so what he does, B will run from 0 to 10, from 10 to 20, C will run because 10, B and C has 10 running time. After that, A will continue. Then it will finish like that. So average turn around time, as you can see, the completion time 10 minus 0, 10, here 20 minus 0, 20, here 1, 20 minus 0 over 3, 50. So in this way, you can see that we get 50 almost compared 110. Now we get 50. That means almost 50%. It seems good. So in fact, given our assumption about job all arrive at the same time, we could prove that SJF is indeed an optimal scheduling algorithm. Okay. So let's continue. Now, problem with SJF with first arrival of A from B and C. For example, the problem with SJF is the arrival time, because in the first assumption we choose all the process came at the same time. But now let's assume A arrives at t is equal to 0 and needs to run for 100 seconds. B and C arrive at 10 and each needs to run for 10 seconds. So what happens in this situation is it become again the same first in first out. Okay, so the problem is because the first process came in is A, so A will run, then B and C will continue. So what happens is the average turnaround time, A completion time 10, arrive 0. Okay, for B completion time is 110 and arrive at 10, and for C completion time is 120 and minus arrive at 10. So now as you can see 103, it become higher. So the arrival time has huge effect. If A comes first, that's also combo effect again, just because of arrival time differences. This is the problem with SJs. So let's continue. So because of this problem, now let's see preemption. Now what we are going to do, short term to completion first. This is the third policy we have. Short term to completion first. So what we are going to do is just we have to add preemption to SJF. So what it does is also known as preemptive short job first. Preemptive short job first. So instead of what it does is any job enters the system, when a new process enters to the system, determine the remaining time of the current running process and new arrived process CPU time. It will compare. For example, when a process is running some amount of time, then when a new process are coming, it will see its burst time. If it is less than with the current running process, then it will be preempted and the shortest time process will run. So schedule the job which has the least time left. So in the context of CPU scheduling, preemption refers to the ability of the operating system to interrupt a running program and allocate the CPU to another process. This is often necessary in multitasking systems where multiple processes compete for CPU time. So let's see. Short term to completion first. Let's say A arrive at 0, okay, A arrive at 0 and needs to run for 100 seconds, okay. B and C arrives at T10 now. So, and each need to run for 10 seconds. So as per this short time to completion, first STCF, what we are going to do now, A will run from 0 to 10. Then at 10, what happened? At 10, B and C comes in. So the scheduler will check how much time will be for B. B needs only 10 seconds. Then it will check with the current running of A. A needs 90 because it already finished 10. So what it does, it will preempt the process A and it will give the CPU to process B. Then process B will run. Okay. Then process B, once it's completed, then it will be terminated. Then process C will continue because again the A needs 90 seconds but C needs only 10 seconds. So B and C will complete it. Then after 30 seconds, process A will come in and finish its process. So as you can see, the A completes at 120 minus arrival time, and B completes at 20, arrival time 10. C completes at 30, arrival time 10. So this divided by 3, 50. As you can see, at least we can get a better. Now, until now we were discussing about turnaround time, but there is another concept came with the introduction of time sharing. Because of time sharing, now we have a new concept of response time. Response time means the time where the first run, when the process get the CPU the first time, and minus the arrival time. Once it comes to in the ready state, the arrival time is there. Then how much time it takes a process to be allocated to the CPU. That is what we call the response time. So because all the processes, once they picked from the long-term scheduler, they will be ready in the ready queue. Then from the ready queue, they will wait to get the CPU. So the short-term scheduler is responsible to choose which process to run. So as per this scheduling, then we have to include in our performance matrix the response time. The idea of response time comes with the introduction of time sharing and interactive system. So the time from when the job arrives to the first time it is scheduled. This is the formula. T response time is first time it is running the CPU, which is allocated in the CPU, minus T arrival, the process which they came in the ready state. So STCF and related discipline are not particularly good for the response time. So they are not good in the response time. Hence the other integrating matrix is the average response time. We shall see, because in addition to average turnaround time, now we have another criteria, average response time. So how can we build a scheduler that is sensitive to response time? Response time is other question. So the fourth policy was introduced. This is round robin RR scheduling. So what it does is time slicing scheduling. Instead of waiting one process completes, something like that. Now in this time we have time slice. Okay. So what it does is run a job for a time slice and then switch to the next job in the run queue until the jobs are finished. Time slice is sometimes called the scheduling quantum, time quantum, and most of the time the timer interrupts every 10 milliseconds or whatever as per the scheduler. So once we have the time slice, the process can run only that slice. Then they will be preempted and the next process will continue. for 10 millisecond, again 10 milliseconds. So all the process, there will be too much context switch. It repeatedly does so until the jobs are finished. The length of a time slice must be a multiple of the timer interrupt period, because if the timer interrupt is 10 millisecond, then 10 millisecond, 20 milliseconds, 30 millisecond, it will continue like that, 40. There will be a lot of context switch. So so round robin is fair, but performs poorly on metrics such as turnaround time. So for it is fair because all the process, they can get equal share, but at the end of the day turnaround time will be poor. It will be very poor. So let's continue. So round robin scheduling example. A, B, C arrive at the same time. All these examples are taken from the textbook, so you can go ahead and check it. They each wish to run for 5 seconds. Okay, so if we are using SJF, what we are going to do? Short job first, yeah. So if they arrive at the same, and if they take 5 seconds, all of them, if they need burst time is 5 seconds, so A will run from 0 to 5, B will be 5 from 10, C will be 10 to 15. So as you can see, the average response, okay, the response time will be A will be, it can arrive at 0 and it get the CPU at 0, so it is 0. B arrives at 0 but it gets the CPU at 5. Okay, so the response time is 5. C gets at 0, okay, but it gets the CPU at 10. So 10 minus 0, again 0, divided by 3, 5 seconds. But if you come to round robin with a time slice of 1 second, what will happen is A will run from 0 to 1, then it will be preempted and B will come. Then B will be run from 1 to 2, then it will be preempted. From 2 3, C will be there, then A will continue, BC, ABC, ABC, ABC. Then as you can see, all 15. So average response time, A comes at 0, get the CPU at 0, plus B at come 0, he get the CPU at 1, plus C at comes 0, but it gets the CPU at 2, divided by 3, then it will be 1 second. So as you can see, the response time round robin is good, but for SJF, the response time, the average response time is bad in the SJF. So the length of the time slice is critical. Okay, the shorter time slice, better response time, it will give us better response time, but what happens is the cost of context switching will dominate overall performance. Okay, because too many context switch will be happen. The longer time slice amortize the cost of switching and worse response time, because the response time will be higher. The cost of context switch is not only due to the copying of registers, but also other architecture aspects like cache, tail, B, etc. So when we say context switch, when the process goes, the progress of the process should be registered, in the, whether in the kernel or in the cache, so many register in the register. So when it continues, all the data should be again loaded in the RAM. So it will be very difficult. It will be, the overall performance will be lower because too many processes are going on. Deciding on the length of the time slice represents a trade of the system's designer. So the fourth one is now, by relaxing assumption 4 that all process can now perform I/O. Until now, we assume that all the processes are not IO bound, okay, only CPU bound. But at this situation, it's not right. Yeah, all the process they need IO bound. So if a process initiates an IO request, what happens? The process state is set to the blocked or wait state. We have seen that diagram. The scheduler should schedule another process in the CPU, otherwise the CPU will be idle and the cost of operation will be higher, because once the process is in the CPU and if it needs IO, if it requests IO request, then it will be it will go to IO request and it will be in the block state, then the CPU will be idle. So to avoid that, what we are going to do is the CPU will be assigned to another process. When the IO completes, an interrupt is generated and control is transferred to the kernel. Then the kernel changes the state of the process that requests the IO back to the ready state. We have seen this by the median scheduler, midterm scheduler. The scheduler may schedule the process on the CPU with the decision of the operating system. So what we can do incorporating the IO by relaxing, as we have seen now, A and B need 50 microsecond, okay, of CPU time each, and A runs for 10 microsecond and then issues an IO request. So IO each take 10 microsecond. B simply uses the CPU for 50 microsecond and perform no IO. The scheduler run A first, then B after. So what we are going to do, as you can see here, if A needs CPU, then if it wants IO, for example, if you do A run from 0 to 10, then after 10 seconds it needs IO request, so it goes to the disk. Then after that, after 20, the IO request is completed. Then after the CPU is idle now. Then after 20 seconds again A will come. Then it will run for 10 seconds. Then again it comes to IO request. Then after it finish IO request. In this way, it will continue like this. Then after it completes, then B will come. Then 50 microsecond, the process will continue. In this case, poor use of resource because the CPU will be idle. But to maximize the CPU utilization, what we'll do overlap allows better use of resource, because when the CPU is allocated to A, and when A runs for 10 seconds, then when it requests IO request and it goes to the disk, then instead of the CPU is idle, what it does is B will be allocated to the CPU. Then it will continue for 10 seconds. Then after that, when A comes, the CPU will be allocated to A, then it will continue like that. So in this way, the performance of the CPU will be high. So incorporating IO, when a job initiates an IO request, the job is blocked and waiting for IO completion. The scheduler should schedule another job on the CPU. When the IO completes, an interrupt is raised for A, in our example. The operating system moves the process from blocked back to the ready state. In this case, in this situation, the performance of our CPU system will be higher. So this lecture slide was prepared by Halo Academy and Brain Boosters. I hope this video was helpful, and we have seen the low level of the high level of policies and different kind of schedulers and its types and examples. So next time we will come up with chapter 8. And till then, bye bye. This is Engineer Selassie from Halo Academy and Brain Boosters. Thank you.